Hello everybody, this is Dr. Heck. I'm looking at problem number 3 from tutorial number 3. In this problem, we're given a mixture of air and H2S gas and told that it's contacted with water in a scrubber. We have the temperature and the pressure. We have the inlet concentration of H2S and the outlet concentration of H2S. We're told that the water is saturated with H2S. And we have the flow rate of air into the scrubber and should determine the flow rate of water. So our general approach for this problem is just a mass balance. We know the total amount of gas that's going into the scrubber. We know the concentration of H2S in, also the concentration of H2S out. That means we can calculate the difference in this amount of H2S in the gas stream. And this amount of H2S has to get transferred to the liquid stream, to the water. And we're told that the outlet of the water is saturated with H2S. And so this means we need to look up the solubility of H2S in water. And this gives us this concentration at the outlet, and the inlet concentration is presumably 0. We assume that pure water is being used here. So where can we get the solubility? This is described by the Henry constant. And here I've taken the values from webbook.nis.gov. This is a great reference, and we can plug these into the expression for the Henry constant. And the Henry constant here is kH, and we should keep in mind the units are given in moles per kilogram per bar. So here in this expression, this is moles of H2S per kilogram of water, and it varies with the pressures. So let's get to work constructing our mass balance. First of all, we have the inlet concentration was 0.12, and we have the outlet concentration was 600 parts per million. We're given the amount was 80 moles per second total gas of air with the H2S contaminant flowing into the scrubber. That means if 12% of this is H2S, we have 9.6 moles of H2S per second that is entering the scrubber. If 9.6 of these 80 moles per second is H2S, this means that the remaining 70.4 moles per second is the clean air, the inert gas. And in the outlet, we know that this 70.4 moles per second, this is staying in the airstream, it's also flowing out. And there's additionally a tiny amount of H2S that's going out here, 600 parts per million. And so if we say we know the flow rate of the inert is 70.4 moles per second, divide this by 1 minus the fraction of H2S in the outlet, then we get the total flow rate at the outlet is 70.44 moles per second, and this includes the inert gas and the H2S gas. And so we have the inlet and the outlet amounts of H2S, the difference between these two amounts. So this is how much H2S is flowing into the contactor, and this is how much is flowing out. And that difference is 9.558 moles per second. And this amount of H2S has to get transferred to the liquid phase. So this is the amount that gets added to the water. And here, this is according to the Henry constant. Wikipedia, for instance, there are different values of the Henry constant. In the Henry law, you have to be a little bit flexible and look exactly what units your coefficient is using. In our case, the Henry constant was given as moles per, if we go back up, we had moles of H2S per kilogram of water and the pressure term. So here, the Henry constant, we multiply it by the pressure, and we have moles of H2S per gram of water. And what we want is a mole fraction, like what we were using for the gas phase. So if we take the grams of water and say that in water there are 18 grams per mole, we now have a mole fraction. So this is moles of H2S per moles of water. This is the balance equation that we derived in class. I'm not going to rederive it here, but in principle we have on the gas side, what goes in minus what goes out is equal to the difference on the liquid side. So what doesn't come out in the gas has to have gone into the liquid, which means in the liquid we have a low concentration coming in and a high concentration coming out. So in the problem we were given the concentration of H2S in the gas inlet and in the outlet, and we were giving the flow rate of the gas, and we know for the inert gas what the flow rate is. In the liquid, we know that the concentration at the outlet is saturated and the concentration at the inlet is presumably 0. And what we need to calculate now is the flow rate of water. What should the flow rate of water into the scrubber be? So to go back to your question, for evaluating the mole fraction of liquid, this is what we were asked in the problem. And in principle, in this balance equation, we always have to calculate it. And yeah, this fraction in the water is the Henry constant times the pressure. The reason we multiplied by the molecular weight is looking at the Henry constant. We looked at what units were used and looked that in our balance we wanted to work in mole fractions. And so in this case, you're going to have to look at that at every problem and pay attention to your units. So I hope this helps. Good luck.